Our speaker this evening is notably passionate about the Google Go language. Please welcome the Principal Software Engineer of Oracle Data Cloud, Aaron Stockton.
I didn't know liking Go was my defining trait until just now. So yeah, I'm Aaron Stockton. I work for Oracle Data Cloud. We are Oracle's digital advertising arm. So I'll try to speak up. I don't think I can shout like that for 45 minutes though. What we do as a business, what my team is responsible for, is we manage the delivery of different data elements to different partners. So that data is then used on different ad platforms for targeting or to drive measurement. So what I'll talk about today is just we started with Cassandra in our initial implementation, obviously ended up with Scylla, had a few stops in between, and then at the end just briefly hit on some client-side changes that we made. So each integration that we have, and just stop me and interrupt if you have any questions. I'm just going to try to frame the problem a little bit that we're trying to solve, and then I'll get into the specifics. So each integration that we have, there's different protocols or implementations, but one commonality is the format of the data that we're trying to deliver. So it's either going to be at a user level, so we'll have every attribute that we know about a given user, or it's going to be at an audience level, so where every user within that audience would share a common attribute. So that attribute might be most likely to buy X or previously bought Y, something like that. A lot of our data is the result of some sort of user interaction. In order to get to kind of the source data that we have, there's a lot of data science that goes into it. But today we're just going to focus on the user level problem because it's harder for us to solve. In that user level problem, we're talking about associating thousands of independently changing attributes to various users. The larger integrations that we have, that's going to be hundreds of millions of users at a time. So this is just an example of kind of inputs and outputs. So the yellow we call our universe. It's just our ID mapping to our partner, whatever ID we need to translate on or transfer on, so that they know how to reconcile the user we're talking about. And the blue is this collection of audiences. So those are all stored in S3, and it's going to be some sort of ID associated with a value. And then the output is going to be at that translated ID level, and then all the attributes and their given values for that. So the output records, okay, we just move off that so I can display. So this is our old system. This is kind of what we're trying to solve around. So it's called batch fulfillment, and it's very much a batch system. It was originally written, I think, 4 or 5 years ago. And it was as the company, which was then Datalogics, was moving into the Hadoop ecosystem. It's really scripted around EMR. So there's a lot of automation that's in place to spin up EMR clusters, to do a lot of post-processing. There's a scheduler that we use that handles the handoff from joining the data to translating it to the relative. We call it taxonomy, but just applying metadata to that. And then each integration has its own kind of delivery mechanics that we have to keep in mind. So the problem with this, though, is when it was initially architected, we had very few partners and not a lot of audiences or attributes that we're actually tracking. So it wasn't viewed as all that inefficient to spin up a cluster per. But today we're spinning up hundreds of clusters a day. They fail for various given reasons. We play the spot game and we lose on that, so we'll abort a job halfway through because we lose the nodes. There's just transient failures in EMR in general that we face. We ended up having to stand up an operations team just to try to help manage this. And what that's resulted in is a lot of alert fatigue for us. A lot of those failures just get escalated straight to developers, which takes away from us trying to deprecate the system. So the faster we can get off it, in our minds, the better. So our new, what we wanted to do was to have some sort of streaming model. So instead of batch fulfillment, streaming fulfillment. So we wanted to take this join that we had, where we would take this list of user IDs and every audience that they had, And instead of recomputing that on a per job basis, we wanted to persist it. We wanted to co-locate that data so we could retrieve it on a key by key, be able to say, hey, for user X, give me all the attributes that you know about it. For our data that, that ends up being thousands of attributes possibly that could come back for a given user. So we came up with minimum specs as far as what would be acceptable for reading, throughput and our writes. We kind of came up with some ideas as far as like that 48-hour start from nothing recovery, not just a failure scenario with hardware, but say we find out we have some fundamental flaw in our data, and the data we have persisted. How long will it take us to kind of reserialize all that data to get back to a working model with whatever corrections we need? So ideally trying to do that within 48 hours. And again, for this system, not the only thing we care about, but we are much more throughput sensitive than latency. So this isn't browser path. We're not counting milliseconds here. The measure of success is going to be how many joins or how many users we can pull back from the data store within a given amount of time. So it's usually time to process hundreds of millions of queries. So we have Cassandra there. That question mark used to be like over the eyeball. It looked a lot better, but that was kind of our initial thought was to go with Cassandra. We have a lot of operational experience with it, so that was kind of our initial stab. We're going an assumption that we were going to use Cassandra. At the same time, with that, there's kind of another part of the team started looking at the in-memory option, or an in-memory option, which I can talk about real quick. So this is the only slide I have about Dynamite, but for those kind of unacquainted with Dynamite, it's out of Netflix. It is a generic Dynamo implementation that can be backed by different key value stores. We chose Redis. I think at the time the only other one was Memcached. But one of the things that was appealing to us about Redis is we have this user ID and a bunch of attributes, and Redis is a data structure store. It just seemed to fit, a set of attributes which are all going to be numeric for our use case. Being able to, the writes, being able to efficiently take what could be in Cassandra, thousands of rows and kind of pivot that to one row with thousands of entries in a set. So we prototyped it. We had 110 R4 XLs. So those are 4-core instances with 30 gigs of RAM. One thing about Redis, though, that even with the Dynamite pairing that we didn't like is with the 4 cores, we're still, Redis being single-threaded, the Dynamite manager was running on another thread. We were leaving 2 cores on the table. So one thing that Dynamite doesn't do out of the box is support running multiple instances on the same hardware. So the other thing about it was, so with this, that's 3 terabytes of memory that we had. We were using 1.8 terabytes of it. It was expensive. And so trying to price this, that was with RF1. So trying to price this to work for our use case in a production scale where we wanted fault tolerance, it was gonna cost, I think conservative estimates were like $70,000 a month. So didn't seem like a viable option after investigating, but it was extremely promising. The performance was extremely impressive. We were able to go backing up to S3, cold starting in 2 minutes. The Redis big key CLI command was able to scan 2 terabytes of data in under 2 minutes. So one of the other things, as far as Redis is concerned, that was interesting to us is there's, we're going to talk about Scylla, obviously, today. And one of the things that came out of Scylla is their C-star framework. And someone actually took that and wrote, it's called Redis, which is a terrible name. It stands for Parallel Redis. But that allowing you to essentially take Redis and split it over multiple cores. It wasn't something that we investigated too thoroughly because we still weren't getting around the constraints of it being really expensive. So this is kind of our focus on Cassandra. We, as an organization, we felt like we knew Cassandra. We have more than a few what we consider to be expert level users that we solicited for advice, trying to help influence the implementation that we were going to go with. But we had concerns from the beginning. It's a challenging data set. And so at the worst case, like the pathological case for this data set would be one key associated with 30,000, in Cassandra it's going to be rows, but those 30,000 attributes, those wide rows. So we weren't sure as far as handling the mixed read-write workload. So Cassandra is pretty good. You know, you can tune pretty easily for the writes. There's a lot you can do to tune for reads, but trying to support both in a mixed scenario, like we were going to try to do, that was going to be difficult. And yeah, just move on. Need water. Seriously, interrupt me if you have any questions. First stab with Cassandra. So we started off with, so we took our footprint as far as what we, the amount of data that we had, and that we tried to use that to influence our cluster sizing. And we went oversized initially. This was hopefully, you know, we could scale down if we needed to, but we were trying to, as quickly as we can, throw money at a problem and flesh out a solution that works. So we started out with 75 i3 2XLs. That instance size, the 2XLs for Cassandra, kind of seems like a sweet spot. With the JVM, you don't usually want to go over 31 gigs because of compressed pointers. You have diminishing returns when you go over 31 gigs. And then with the 8 cores, we felt like that kind of left enough computation on the node to handle whether it be repairs or running compactions or just a heavy read-write workload that we're going to have. We also tried going up by a third to 100, and then we tried going wide with Cassandra. And this is our schema right here. So we have ID, which is numeric, the audience ID as well. Audience type is going to be enum, and then our source value is alphanumeric. It's all T for true in this use case. So we loaded 40,000 full-size kind of sample audiences. We have 60,000 in practice, and we just tried to see how it would perform in a read scenario. So we hit it with a few different clients just to test out Cassandra performance. Spark SQL, Spark Streaming, and then Akka Streams. There's some interesting characteristics between that we saw the clients as far as the stress that they put on Cassandra in different ways, but ultimately we were not able to scale past hundreds of wide rows, so hundreds of keys coming out of Cassandra per second in any of those cluster footprints. So this is our first kind of the tech on the right is our first like hardened implementation of what our read path looked like. We had Akka Streams, consumer reading off Kafka using the Java data stacks Cassandra driver with using prepared statements, hitting Cassandra, and yeah, it was not working well. So we could bootstrap pretty effectively. We had some internal tooling kind of that in support of us feeling like we knew a lot about Cassandra. There's this quick bootstrapping use case with something that other teams have had solved before. So we kind of piggybacked off their solutions, and we ended up with something that could read, thousands of source files from S3. We into Spark data frames. We'd serialize SS tables on our Spark executors, and then in process we'd run SS table loader to stream the data to Cassandra. So it was actually, the bulk loading was extremely fast. We could get about 15 million user attribute pairs per second, so 15 million rows per second. But when we tried to do this while running reads, it cratered. So just bulk loading, it was fine, but we would see multi-second GC pauses. And if we're not trying to run reads at the same time, and we're seeing failures on the bulk load, failures that we're going to retry, we didn't care too much. But we're also trying to think of the use case where we're constantly appending data to user IDs. So we would have this bulk load process running as new data came in, or we thought of a lot of different scenarios, but maybe building up a batch before we would bulk load. But it needed to be able to do that while we ran reads against it, and it couldn't. So then we moved to, instead of trying to go through SS table loader, we just tried to going through CQL. So our performance and writes went from 15 million a second to about 140,000 a second, and that was writing at consistency level all, going through CQL. So going through the front door instead. The reason we were at consistency level all was we wanted to limit repairs. We wanted to be able to have recent data also for our reads, and to retune it, we wanted to be able to read at a consistency level of 1. So to be strongly consistent, write at all, read at 1. So one job in this scenario would take about 2 days to complete. That was with a light. I was going through the front door. We couldn't get it to complete at all if we're running the bulk load process. So that was We used Spark Cassandra library in order to go through CQL, and yeah, it was pretty problematic. A lot of times, even with that, we would lose too many nodes to finish the job anyways. So we kind of hit a wall. This is a block of text, and I put it up here just because it really represents us, the tuning things that were recommended to us by, we worked with a Cassandra consultancy, and the consultancy is definitely made up of what are unquestionably Cassandra experts. They definitely know their stuff. They had some pretty good learnings that we were able to take. One of the things is that we were, in one of our tables, we had a compression chunk length that was longer than the average row of our data, so we would decompress data and then just throw it out the door because it wasn't associated to the key we're pulling. Just things like that, but it ended up, even with all these kind of suggestions we got from them, we didn't have a stable use case. They thought we could actually decrease our total node count by at least 50%, which was troublesome because we didn't have a stable use case anyways. But so we saw limited improvement, definitely incorporating all these into our workflow. But at this point, we've made it pretty far with the tooling we had around Cassandra. We felt like our client applications, as far as writing to it, the reads, as far as we put a lot of work into just the application in order to process that data downstream of it. We were just having a pretty big issue with Cassandra at this point, so we kind of hit a wall. So giving Scylla a shot, a shards man. So Scylla is SQL compatible. So the drivers that we're using for Cassandra worked out of the box with Scylla. Scylla actually doesn't ship their own driver. So that is definitely an intention of theirs to maintain that compatibility with Cassandra. So Scylla, I'll just real briefly go over. It's a sharded, shared nothing architecture. So once a query arrives at a node in Scylla, there's another level of distribution that determines what shard, and a shard is associated to a CPU core, or to a CPU. So it determines what shard it goes to, whereas Cassandra really only has that distribution level at the node, distribution layer at the node level. So once it gets to a node, there's no other layer of distribution. It has to deal with a lot of concurrency primitives in order to handle multiple queries at a time. So those Java concurrency primitives that can be kind of tricky is that picture on the left. So one of the reasons that we were kind of excited about Scylla, other than kind of the shared nothing architecture, was a lot of the wins that we had in tuning Cassandra came from tuning the JVM. And a lot of the pain we felt with Cassandra came from the JVM. And so we were curious to see how Scylla would kind of fit in that, kind of eliminating that extra layer of virtualization from it, removing the JVM from the picture. So we just dropped it in. All we did is replace Cassandra with Scylla, and we went from hundreds of reads a second to thousands. And this was, deadlines were inching closer. We felt like we didn't have a whole lot of options as far as, so this was kind of a last-ditch pivot, and it was extremely promising from the beginning. Again, we didn't have to change any of our application code in order to work with it. There's changes we made later on in order to kind of optimize for the Scylla use case. The initial Go edit was an apples-to-apples comparison. We wanted 75 i32XLs to see what it would do with the hardware, how well it could run our workload. So it mentions shard balancing problems once it got to Scylla. That was because there's a default in an older enterprise version that we were using. That default's changed, and once we fixed that, that wasn't an issue anymore. So after we dropped it in, like I said, our throughput went increased by an order of magnitude. It's close to 40x what we saw. So we have, in this picture, we have our writes are orchestrated. We're using the Spark Cassandra library. The first thing that we noticed off the bat was just dropping Scylla in there, like forget the performance improvements that we saw, we stopped losing nodes. So we were actually, if nothing else improved, like changed, other than the fact that we didn't lose any nodes, we probably would have made the switch anyways. So it was painful enough to manage our Cassandra cluster. Losing nodes, what would happen to Cassandra, the reason we were losing nodes is the GC pauses would exceed the gossip timeout, and Cassandra would boot nodes from the ring. And so we would boot enough nodes from the ring that data ownership became a real issue. We're reading a consistency level of 1. We couldn't find a single replica that owned a key. And so we'd fail these jobs. So at this point, just
never lose nodes.
Say that again?
So you never lost nodes in Scylla?
I haven't yet. I mean, there's other parts of our organization that are in a different environment that have had like hardware failures, but I've never toppled a Scylla node.
But with the sharding, wouldn't that make losing a node much more painful?
Why?
Because the data is split out with the shards. What if you lose one of those shards?
So the replication is still at the node level.
Okay.
So if you have an RF2, that data is still going to live. So there's not like affinity within Scylla for, it's not going to co-locate replicas on the same machine just because it has the shard.
When you say losing a node, do you mean like setting a responsive to like CPU spike? What do you?
No, so Cassandra would boot it from the ring. So the node, like you could log it, you could jump on and it might look fine. It's just not a member of the cluster anymore. But we also, I mean, we lost some nodes were unresponsive, but mainly it was gossip timeouts that were killing us.
You said you were able to do like lots of reads at some rate. How are joins?
Say that again?
How are joins?
How are joins?
Like, you're able to do reads at a certain rate.
I can't hear. I'm sorry.
You're able to do reads at a certain rate. What about joins?
Yeah, I mean, so the read is our join. We're joining it to our source data.
Oh, okay.
So yeah. Yeah.
Are you basically not have cluster?
Not in this use case, no. So we're consuming from Kafka, so they're all Kafka consumers. So Kafka is kind of the orchestrator for that. They all are part of the same consumer group. Cool. All right, so one of the limitations that we found at this point with Scylla was our bulk loader that we were pretty proud of didn't work. So the SS table format for Scylla that we were using is, I think, 218. We were using Cassandra 311. The interface from 2.x to 3.x and SS tables changed enough where it's going to result in kind of a non-trivial effort to downgrade our bulk loader to work with the old SS table format. But what we found is that it wasn't as much of an issue as we thought it was going to be. So going through, I keep calling it the front door, but going through the CQL driver, we were able to get 10 million writes a second at consistency level all, compared to the 140,000 that we're seeing against Cassandra in the same vein. So this slide is called tuning Scylla, which is kind of a misnomer because Scylla really touts itself as a self-tuning database. So what it does, it'll profile the host when it spins up and try to make intelligent decisions and defaults based on kind of the hardware that it's running on. So what we found is a lot of the Cassandra configurations, the knobs that we were used to turning, they either were gone altogether or they were just nerfed. They didn't do anything. So one of the things that we liked about our experience with Cassandra that made us feel comfortable about it was felt like we knew what to monitor. So we had dashboards set up. We were monitoring GC times. Where it just felt like we had good insight, good telemetry into Cassandra operations, and we were a little worried about that with Scylla. But what we found out was that it ships really rich Prometheus metrics out of the box. So there's a Prometheus exporter. We just pointed our Prometheus server to scrape those. And then they have dashboards in a GitHub project that you can just import into your Grafana instance, configure your data source, and you're good to go. You're up and running. So we had to make small modifications to that, but it was pretty minor. So again, the monitoring per shard, since Scylla or the C-Star framework that it's kind of built on. I think Scylla was written first and C-Star was extracted out of that. But everything happens on a per shard basis. So if there's imbalances, if you're hitting one shard more than another, then really being able to monitor that and see that, which was a lot of our issues, a lot of performance gains that we had. We're fixing, pinning things to shards. And then this diff down here is a patch that we applied to the Java DataStax driver. So what we found was that the DataStax driver has an affinity for the first connection. So our throughput through the driver actually wasn't high enough to make it move off the first connection. So what Scylla does is every connection that you create to a Scylla box, it's going to bind that to a shard. That shard, so it's that shard handles every request coming in on that connection. So if you only hit one connection or send requests on one connection, you're going to be pegging that shard with every request. All we did is we added a really dumb round robin. So the driver in here has this idea of least busy connection. And so since every connection seemed like it was the least busy, they were all unbusy as far as the driver was concerned, it never moved off that first connection. So we added this round robin that would just force it to start on the next connection each time it was making a request. We stole this from another Cassandra driver that was written in Go that I'll talk about in a bit. But this right here was all we needed. There's one more line where we're declaring the atomic integer starting connection. But outside of that, making this change made a world of difference as far as balancing across shards for us. So the last model of ScyllaDB, we had gotten pretty far with it, but we still, we had these imbalancing issues. We weren't getting full utilization on these boxes, so kind of a blessing and a curse of their of the monitoring and metrics you get out of it is it'll tell you pretty clearly. We had a lot of our cluster. These are shards, so CPUs that are sitting around 50%. We're pegging 2 of them, and we didn't know why. So the graph on the left is actually the result of speculative retries. So just for those unacquainted, speculative retries are if you send a query to a node and it doesn't respond and it's configurable, it can either be time-based or on some percentile. So say that query doesn't return within 5 milliseconds or within whatever your 99th percentile is, then whatever's coordinating that query can either be client side or server side. In this case, it was server side. Is gonna send off another query, and so whichever query comes back first wins. So what we were seeing is we have like the pathological input that we have. Maybe that lived on, say, shard 2. So shard 2 houses data that's much slower than or much larger than any other shard. Say that's kind of our absolute worst case scenario. There's 30,000 rows associated with the key on shard 2. So you're reading that row, or you're reading that key, and it doesn't come back within 5 milliseconds. So you fire off another read. Well, it's going to go to shard 2 on the next box that it hits. All those queries that are then going to shard 2 outside of yours, because you're not just hitting it with one query at a time, those are going to pile up because it's waiting on that query, that result to return. So those are going to send off a speculative retry. And there's this cascading effect where we would just continually speculative retry, and it's all bound to the same shard. The simple solution for us was just to disable speculative retry. We aren't, like I said, we're not latency sensitive. We don't really care about milliseconds. So we want as much throughput as possible. If one key is slower, then it's slower. It doesn't matter. We don't want this effect where it's kind of a cascading latency spike. So we're queuing all these SS table reads. One shard is getting hit way harder than the others. Another thing that the guys from Scylla that are in the audience, by the way, I don't know if you guys met Dor, Glauber, but Glauber came out on his way to Austin. I don't know if I said that earlier, but he was talking to me about the SS table format in Cassandra 2.x, which Cassandra's on version 3 right now. They're 2.2 or 2.18 compatible. I don't know what it is in the open source version, but it's pretty inefficient the more columns that you have. So it repeats the column name for every row. So we moved this 4-column schema into a 2-column schema. So we just collapsed those last 3 columns into a protobuf object. We handle serialization and deserialization on the client side. And that audience tuple is just a blob data type, so just an array of bytes. That right there got us an extra 10% performance just by doing that. And then lastly we disabled our cache. Our read pattern is we're reading every key, every user associated to a certain partner, and never twice. So caching didn't make a lot of sense. So trying to keep that cache up to date was a waste of time. The cache hit rate was ridiculously low. Disabling that also got some more performance. I have on here too i316XLs. I don't think I have anything on there to talk about it. So Scylla does well with larger boxes, whereas Cassandra, kind of that sweet spot might be like 60 gigs of RAM. You can always just add more nodes in a Cassandra system. Scylla does a really great job of scaling vertically. So we went from i32XLs, we went down to 72 i32XLs, and then we went to 36 4XLs, and then 18 8XLs, and then we tried moving to i316XLs. The issue with that was we had a decent beat on bouncing the connection across the shards with the i3 8XLs. For some reason, we weren't able to quite tune it for the 16XL. So the reason that the move for the 8XL to the 16XL was intriguing is Scylla reserves 2 CPUs for network interrupts. So that's a penalty that you're going to pay on every node. So if you have on the 8XLs, you have 32 CPU, then you're only going to have 30 active shards. Whereas on the on the i3 16XLs with the 64 CPU, you're still only reserving 2 for network interrupts. So you're paying for the same number of CPU, but you're getting more with the 16XLs. We couldn't handle the connection balancing, so we ended up punting on that. Are we there yet? Man, our product was asking this question every day. This was a long journey that we had, kind of going through the Cassandra stuff, the pivot to Dynamite, or that was kind of improv at the same time. The pivot to Scylla, which trying to explain to them, it didn't take any code changes. They were really pushing us to get something out to production. So at this point, our application is stable. We went from something that took us over a day to run to with the Akka Streams client, we're able to do it in just under 6 hours. But we feel like there's still more performance to be had. So this was a larger change that we made. So we pivoted on our client implementation. So I started looking at different CQL clients to see how they handled connections, just because I hadn't looked closely enough at the Java code yet to verify how hard it would be to balance those myself. And I saw in the GoSQL library that it advertised that they round robin connections, and then digging in, it was a really simple round robin that, as far as sending queries down connections. So we pivoted. We kind of started prototyping in Go. We got more momentum with it, and ended up pushing that out to production. So we ended up, our current implementation is running with about 20,000 keys a second. And one of the telling things that or more interesting problems that Go solved for us, which was kind of by accident, maybe completely by accident, if I'm being honest, was our client application in Akka Streams was churning through a 31 gig heap really quickly. It was a really healthy seesaw GC pattern, but it was spinning a lot of cycles GCing. And that was because if we're doing thousands of reads per second, that means we're pulling back millions of rows. We transform those rows, we're dropping some off. There's a few intermediate stages that row is going to take, and then the final form could go out to 3 or 4 different Kafka topics, and it's just, it seemed, it was slow. So rewriting it in Go, one of the benefits that we kind of fell into was Go doing escape analysis at build time. So I was unaware of this until I kind of dug into it more. But so what escape analysis is Go is going to take a look at each stack frame, and it's going to determine whether or not a variable escapes a stack. If the variable escapes a stack, it needs to go to the heap, and it's going to eventually be garbage collected. But if it never escapes a stack, it can be thrown out with the stack. So all these intermediate forms that our data was taking, the only one that mattered was the final one that was leaving the stack. So we're able to throw away gigabytes of data just with the stack. it natively kind of fixed our shard balancing problem without having to run our own patched driver as well. And yeah, so this is just an example dashboard that we have of our client application. The top one is just demonstrating that we're churning through it in about 2 hours. The memory used per client is, per Go client is about 3 gigs or less. And then, yeah, we're churning through. So this one, we're pulling off, you know, around 8,000 messages a second. So, yeah. And then this is just an example of the kind of or visualization, the view you get in Scylla, and then stole that from YouTube. Scylla DB is web scale. All right, so it's just a recap. So Cassandra, we still use it heavily internally. It's not like we completely abandoned Cassandra. We have a lot of experience with it, but the problems with white rows and garbage collection, it was something that we weren't able to solve. The other thing that we saw as far as the difference between Cassandra and Scylla was these i3 instances that have huge, the NVMe volumes that are so capable with disk seeks. Cassandra is not saturating with the disk at all. Like it's not taking advantage of what you're giving it. Dynamite, what we found, it was incredibly fast. It's pretty promising. The Dynamite manager, the sidecar that comes with it, needed some tweaking for our use cases, but ultimately, yeah, it was just way too expensive. And then Scylla, the Cassandra compatible API was a huge selling point, enabling us to pivot to it. It handled our throughput requirements with wide rows. The support that we got from the Scylla guys was seriously, it was world class. I mean, their willingness to dig into to help you think about your application code, really digging into tuning the driver that they didn't write, recommending things, and then just their knowledge in general of systems is pretty incredible. So, with that said, I just want to shout out to Glauber Costa, who's in the back, and then the rest of my team is on board, and I can take any more questions if there's any. Sweet. I'm off easy.
Questions, anybody?
So the white rows problem, was that a Cassandra problem or?
Yeah, I mean that was, we tried rethinking our data model a few times because the wide rows was an issue. And we're like, okay, if it's wide rows, maybe that's the issue and not necessarily Cassandra. So is there a different way that we can structure the data? The fact is that that's how we need to deliver that data. So we'd rather try to create this whole other post-processing thing to stitch all this data back together, or we could store it co-located.
Cassandra can support white rows, right?
Yeah, and we actually have, so it was wide rows with high throughput. So we have use cases that have gigabytes of data associated to a key, or a gigabyte of data associated to a key. So it's not necessarily the wide rows. It was wide rows and high throughput that we were going for, and that's kind of where it's topical for us. Anybody else? Yeah.
Who makes the decision when finding things to pivot?
My boss, I guess. I mean, we ran into Scylla at AWS or at reInvent, and that was kind of, we as an organization had already actually had tried out Scylla before, and it wasn't a fit for the use case that this other team within our platform was looking for. But that was kind of fresh in my boss's mind, and he said, "Hey, have we given Scylla a shot?" We had automation, we had Terraform automation where we could get off the ground pretty quickly with a Scylla cluster, so it was a pretty low effort pivot. We just had to change IP addresses in our configuration.
So it was like great after
Oh, for sure. Yeah, I mean, we couldn't have gone to production with Cassandra. We probably could have, the amount of money that we would have had to throw at it, we probably would have been better off going with Dynamite and Redis and like an in-memory option. We could not get it to scale.
So, sorry, I missed the beginning of the discussion. You already covered it. You mentioned problems with things like rights and reads with Cassandra. Do you think that was a Cassandra problem or the combination of Cassandra and your data model?
Yeah, I think the wide rows the wide rows played a huge part in that, right? So one of the things that the consultancy, the last thing they wanted to try was running a custom Cassandra jar that would print out every tombstone that it came across, like so their recommendation then was going to be, okay, so maybe don't delete data, which wasn't really an option for us. It's definitely our use case. Maybe we were stubborn with it, right? But we knew kind of the format that we wanted the data structured in, and we really, honestly, we were all surprised that Cassandra wasn't going to work for this use case specifically. We have a ton of stuff running on it, but it's probably a mix of the two.
Gotcha. You mentioned tombstone. Were those talking about the white rows,
Mhm.
being tombstone, and then just kind of hang out?
Yeah, so we wouldn't just append data to it, but like we'd also remove attributes from users. So we'd write tombstones again at consistency level all, so we could read at one, try to limit needing to do repairs.
What different about the other use case that made Scylla not a good fit for it?
So it was actually I think Scylla, I have to talk to them again, but it was over keys that it's a good fit now. So they fixed it. I think they fixed it, but it was an issue with keys with more than like 4K data associated to it, is what the issue was. So that was maybe a year ago. So these guys move fast to try to fix problems. Yeah.
I guess that's the next question. Except for this question is that you end up kind of having the key value pair data structure, and so you had a mutation. So you wanted to change the values which are associated with keys, but they are still key values. So like you collapse the all columns and other stuff, and so you never had a use case of searching from secondary key, like any other only a key value.
No, anytime we were pulling data out, we were pulling every row associated to it, so we didn't need to kind of filter more. We could, provide that the blob, if we're trying to verify like membership, that an attribute exists, but it's not a use case that we have currently. But it would still let us do that even with the serialized, kind of collapsing it all into one column.
And one more thing is that Cassandra was supporting column families, right? I don't remember exactly. But so was that going to help your original data design, schema design of wide rows with the column families?
So I don't understand the question.
So,
Sorry,
I guess the wide row problem was you have more columns.
Sure.
Yeah. You tried out the column family approach, or was it
Like the thrift-based approach for Cassandra?
Column families, like
So the column family, right, is the CQL analog is a table for Cassandra. So it's we tried various schemas, but
So when you say wide rows, how we wide rows wide by the amount of data, or wide? Well, you didn't have that many columns. So
yeah. So it was the number of rows associated to a single key.
okay. Okay.
oh, sorry.
Can you have an idea of the growth at the beginning? How much money did you save?
That's a good question. I don't know what the license cost. We pay for Scylla, so I don't know what the license costs that we're paying. Hardware, as far as hardware goes, we never got to a point where we could actually say this is how much it would cost to run Cassandra, because it was going to be way too freaking big to try it out. So my guess is still just a lot. I don't know.
Sorry if you already covered it. So you said that Scylla performed a lot better with wide rows. Was the schema remain the same at all? Like, was it a
Yeah, it was.
migration?
It was apples to apples comparison, schema and everything.
Okay, so it's just has to do with the database itself.
Yeah, it was. So in our case, it was the GC pressure that it put on Cassandra, pulling millions of kind of transient objects out a second, passing those through the JVM. It was a problem.
How about we do that? Hi, I'm Andor, I'm co-founder of Scylla, and this is Robert. He's our new VP of field engineering, and one of the best developers we have on the team. So what I suggest to do is let's continue to have this Q&A. We have the potential data we can give you about how we build Scylla. Scylla is open source, so you can either go through the internals or just continue to answer Q&A. So let's continue with the Q&A, but I think that it will be good that Glover will answer it, so we can probably answer pretty much every question that you guys have. And of course, questions to Aaron, you're welcome to ask Aaron as well.
While we set up, just out of curiosity, is anybody here using Cassandra these days? Or you guys, anybody who's already using Scylla? Yeah, I mean, why we set up? If you want to continue the Q&A, any questions they ask to Aaron that I could answer, Aaron can keep answering.
So we know that Apple has something like 100,000 Cassandra nodes. What makes it that we don't have that they're migrating to less?
I gotta ask them. We do have, as you can see, a lot of high-profile customers. It's a very biased question because if you ask me, I obviously, obviously, I would love everybody to migrate to Scylla like today, right now. We can help you actually if you have 15 minutes outside. But if you look at the history of Scylla and if you look at our users, why this one particular user that you mentioned is not using Scylla to the best of my knowledge, plenty of others are. In their case, it might just have to do with the fact that they have a lot of committers to the Cassandra project, so you know it's stuff that they know pretty well. It's actually a great slide for us to start. This is some of our customers. We have recently published a very nice use case with Ola Cabs, Grab as well. So both companies, they're competing with Uber in Southeast Asia, in India. That's the case for Ola Cabs. We have companies from a lot of verticals. We have a lot of companies from the ad space, like they are, and like look, migrating. If you already have a database in production, migrating it's not simple. So we definitely understand that it takes time, but we do have a lot of confidence in the product that we built. And what I would like to do, like I'll skip most of this deck, but what I would like to do is, like Aaron told you about the experience they had with Scylla, and the very impressive numbers that they had, as they said, like 20,000 keys per second with very wide rows. So that the equivalent was, like, if I'm not mistaken, 200 million rows a second they were reading from disk with Scylla, with like 16 nodes. The time that I'm going to spend here is telling you like how we do this. Some design decisions that make Scylla what it is.
Maybe just a couple of more questions, just so we'll just answer your question instead of throwing you a very interesting deck.
All right, question there?
Is there anything part of the project named Redis?
There is, yeah. We have a tool to test file systems, basically to stress Scylla, to sit on the other side of Scylla, called Redis. Yeah. Okay, so this is like a very simple comparison. Like Cassandra usually cannot utilize multi-core efficiently. You end up with this sea of very big machines. Scylla scales linearly. We've been using Scylla. We are soon to publish a blog. Scylla's performance on the new i3 Metal from AWS 72 CPUs. We scale this perfectly. And we scale out as well. You've seen Aaron speaking about they did use Scylla with a lot of machines. We provide very consistent latencies. Cassandra is more on the roller coaster side. And one of the things we pride ourselves, and actually I will focus most of this quick presentation on that, is that Scylla is totally auto-tuned. And that's not just got good defaults, that it's not just like this one thing that was set for you in the configuration file. There's a whole host of algorithms. So there's very interesting technology inside Scylla to make the experience of using Scylla hassle-free. You've seen a slide from Cassandra, all the stuff that you got to tune to make Cassandra work well, and there isn't one really for Scylla. There's stuff like here and there they're going to play with, like with data modeling, any workload, but in terms of the actual workloads, no tuning. And you can also run, like they're running Node2 Compact every day, compacting the entire 8 terabyte data set per node in 2-3 hours. and that doesn't affect the foreground. The load is still running. They're still serving 200 million rows a second with this compaction running. I'll tell you more about how.
In general, if you tune it, it means a bug from us, from our perspective. It should be automatically tunable, and we're also about to automate the amount of parallelism and load balancing connection from the client side. So we're working on this too. And about wide rows too, we already developed several improvements for the way that we cache things. So we'll work in a row level granularity. So soon, accessing wide rows will be exactly the performance that you'll get with narrow rows. We're almost there, and it'll get better and better. You had a question over there.
That's right.
That statement about running compactions while running at full speed, is that before or after switching from using the DataStack driver using those?
That has actually not a lot to do with the driver, and more about what's actually in Scylla with the controllers. I guess the version that you guys are running doesn't have the full stuff yet, so I'm going to talk a little bit about what's in there, and we can obviously talk later more about like when it. So you probably are seeing a little bit of disruption, but not a lot of disruption, I would expect. And if you're seeing a lot of disruption, I'm surprised you haven't talked to me yet. But this is like real quick, the stuff that Aaron presented about, like this is like ingestion time for the i3x large, 2x large, 4x large, and the data set is doubling every time I move from one instance to the other, and you can see the ingestion time for the data set twice as big is about the same, so it scales out, scales up, scales out. This is the time to compact the node. Again, the data set, as we move to x large, 2x large, 4x large, 8x large, data set grows, gets twice as big. And with that, like the time to do it is about the same. This is just time to recreate a node, about the same as well, regardless of the instance size. This is like another customer. All right, so I would like to focus a little bit on how we do the things we do, so you understand that this is not magic and this is not just tuning, not just like good defaults that Scylla puts in. Like it's one parameter here that if I happen not to do, I'm not going to have good results. The first one, I think, it's very quick. Aaron already mentioned that we have 2 levels of sharding. So the data is sharded to the node first, and it's replicated the same way as Cassandra. But once we take ownership of that data, say this belongs to this node, I'll do a second level of sharding, and now only one CPU at a time is going to be handling that data. And the result of that is that we can achieve like 100% efficiency in the CPUs. There's no locks, there's nothing in Scylla ever doing any kind of bus locking, mutexes, waiting, or anything like that. So that even the memory allocator, we had issues in the past with the glibc, in which the glibc would take locks. We fixed and we shipped our own glibc for while we needed, and then moved that upstream. So our goal is to do like a 100% from start to finish. One CPU has the request, it processes it. We use asynchronous I/O very heavily, so we never do any blocking operation. This is a part of the C* framework. Aaron alluded to the C* framework in his talk. Is this thing that kind of co-evolved together with Scylla. As we wrote Scylla, we also wrote this framework that can do a lot of the things that Scylla is doing. A lot of that is done through the C* framework. So it's a completely asynchronous framework. You're never going to have any blocking operation. It's basically every core, every CPU in your system running one thread, one event loop, and processing requests as fast as you can do. Blocking is like wasted CPU. We are very close to the hardware, so we wrote, as I said, if Scylla has its own memory allocator. And why is that? Because if we're going to use the system memory allocator, the system memory allocator might take a lock, might block. We don't want that to happen. So that is extremely NUMA friendly, which is one of the reasons we can use those monster machines. Because once we allocate memory, that memory belongs, we allocate the whole chunk from the system, assign that to a single CPU, it's all local, and then from that point on, Scylla's going to manage that internally. We have our own disk I/O scheduler, we have our own CPU scheduler now, coming in version 2.2, which is one of the things that you're missing, and we have our own cache that bypasses the Linux cache entirely. So the reason I like this slide is that the first time people hear about Scylla, what a lot of people think is, okay, they took Cassandra, they rewrote it in C++, And then they claim that they're 10 times faster. How can that be possible? But the gains are not, some gains are definitely coming from the lack of the JVM, but a lot of that is just like our architecture, how we do things, the component and the level of technology that we put in the database and how close to the hardware we get to provide those results. So Aaron did mention, just a quick comment on this, and that was actually one of the questions in the trivia. The i3 16x large instance from Amazon can read at 15 gigabytes a second. Scylla can use it. We have a testimonial in your website from the head of product of Intel Optane. Intel Optane is like probably the fastest drives around these days. His words, not mine. Scylla is the only software out there that can actually bottleneck that drive. And again, that's not because of C++, that's because of this architecture, fully asynchronous, non-blocking, and etc. I'll just keep this. It's not Aaron's use case, but throughput is easy. As you could see, it's not that easy because when you want to reach like extremely high throughputs, most databases out there they won't just. There's always a problem. Like Cassandra wasn't stable. The other, if you go in memory, it's too expensive. But what I used to say is like Bruce Wayne can get any throughput he wants from any database. And why is that? Because it's all a matter of money. Aaron himself has said, I mean, if we had more money to spend, if we wanted to spend more money, we can keep adding nodes and nodes and nodes and nodes and nodes, and at some point, this will perform. So while we take a lot of pride in getting very high level of throughput, very stable, you don't usually see with Scylla the problems that you see out there, it's still easy compared to latencies. Latencies are super hard, and we believe that if we provide like super good latencies, everything follows from there. So just a quick question. Latencies usually, I'll skip through most of that, but I'll keep this one because I like this slide. There are many names for probability distributions, and when we talk about latencies, you don't say a number. Like you never say my latency is 2 milliseconds because there are many percentiles, right? So you can have 2 millisecond average latencies with 100 milliseconds, 99 percentile latencies, 95 percentile latencies. And if I can get you like one message through today is this: what is the name of the distribution for which the high percentile latencies are much higher than the average? Anybody knows? It's not the Gaussian distribution. Like the Gaussian distribution is about what? No. Well, yeah. There are many names, right? But we have a very special name for this distribution in Scylla, where the high percentiles are much higher than the average. We call it a bug. So if you happen to have there, and again, it's software, I'm not saying it's never going to happen. There are also valid situations, like if you're reading a lot from cache and some from a slow disk, you might have, but the database is not going to introduce more latencies to that. I'll skip through most of that. This is like one example we did for auto-tuning things. So one of the issues that we have with Cassandra is that Cassandra acknowledges requests from memory, but then later on you got to write those requests to disk. And the disk tends to be slower than CPU memory. So when finally you have to write those to disk, you have now a massive queue if your writes are still like, and again, the way people handle that is tuning. Like, let me write a little bit less, let me write a little bit more. And the way we handle that with Scylla is by dynamic algorithms. And again, I mentioned before that when we say auto-tuning, we are the autonomous database. We're not talking about good defaults. We're not talking about, hey, this configuration file already comes, although it does. It already comes with good values for the things that you can change. I'm talking about dynamic algorithms. So in this one example here, for instance, we're tackling the problem of I have a disk that is much slower than the memory, much slower than the CPU, and then the requests are accumulating, and your database is going to crash. That's just physics. So what we do instead, again, we are close to the hardware, we're bypassing the Linux page cache, we write directly to disk, and because we can do that, we can know exactly at which speed we're writing things to disk. So the buffer fills, when the buffer fills, that means I'm not writing fast enough and I start to throttle requests right there. Not until the buffer goes empty, but until I free enough resources to admit the next request. And by doing this, instead of having like the 99 percentile 22 times higher than the average, what are those requests? The requests that stopped while the database was trying to figure out what to do instead of crashing. And I have this instead. which is like 5 times higher than the average. Just because instead, if you look at the mean, the mean is much higher now, but what I did is that I moved all your latencies closer to each other, and then you can look at that and know for sure, this is the latency that my system can sustain, and all of that without any human intervention. You can see the graph here, and we start kind of high because it's still in memory, it's still the things that are coming from memory, but then automatically, again, we're the autonomous database, without any human intervention, I brought you to disk speed. This is like when Aaron said like Scylla self-tuning, this is what he's talking about. This is the value proposition that we have. You're not going to have to be tuning your system ad infinitum, like change this, change the GC, change the compaction strategy. Or the compaction strategy you do have to change because we change the compaction bandwidth and etc. So I'll just skip through this because it's not very interesting. This one is a lot more interesting though. So we do, one of the things that I mentioned that we have is an I/O scheduler inside a database. So we just set all the Linux disk schedulers to NUP. We're not going to let Linux do any kind of reordering. We do this configuration automatically for you when you start, basically setting proc files, and then we have an I/O scheduler inside Scylla. It lives inside Scylla. And the reason we do this is that every SSD, every modern SSD disk follows a pattern, follows a curve more or less like this. As you start throwing more requests in parallel, that's here in the x-axis, the disk gets faster. But this is the eternal enemy of databases. There's this thing called physics. You can't really go further than the throughput limit of the device. Once you hit that, there is no point in adding more parallelism. You only add latency, which is the red line. So what we do instead is that before you start Scylla, we're going to benchmark your disks, and we're going to find that point. So we're going to know what that point is. And we know that it's useless to send requests after that point. They're going to get queued in the device anyway. And if they get queued in the device, I would rather queue them than myself. Why? Because then if I queue them, I can tag them. And I can say, this is a query request and this is a compaction request. That is what allows me to run compactions at full speed and finish an entire workload in a couple of hours. Because if a read request comes, I can have 1,000 requests queued in the compaction queue. I don't care. They're not going. My query is going because there is some algorithm there that is determining how much of the bandwidth should each of them use. Again, all of that fully automatic. So the I/O scheduler is something that works very well. In Scylla 2.2, which you're going to start using soon, Matt, we're also enabling the CPU scheduler. Why is that? Because with modern disks, like the i3 disks, sometimes the disk is so fast that the bottleneck shifts from the disk to the CPU. And because the tasks are all ordered and the CPU is still in FIFO order, you can start having isolation breakages if you are CPU bound, which was something very hard to achieve 5 years ago, but it's becoming common now. So we also have to bring into Scylla a CPU scheduler to do something similar. So inside the event loop, inside the Scylla reactor, we'll tag stuff and we'll say, okay, compaction, you can have as many requests in parallel as you want. When I have a query, I'll run the query, and then you're going to be able to provide QoS between queries and compactions and everything else as well. That's awesome. Isolation is great, but being the autonomous database, being what we are, striving to what we want to do in Scylla, we want to do more than that. It's not enough for me to provide isolation. I also want to do dynamic algorithms in those priorities, to be shifting those priorities in runtime without you having to tune anything. So basically what it does is that based on something that I'm going to explain very briefly, if I see that this priority is not the ideal priority, and we have a very nice blog post that I published recently explaining how to get to those conclusions, I'm going to adjust my priority of my class higher or lower until I get to perfection. This is very similar. This is technology that we're bringing from industrial controllers. It's very similar to the technology that you have in your car to do cruise control. Instead of like, I don't know what's the torque that I have to apply to each part, but I know that I want to cruise at 66 miles per hour, and then we apply control theory, which is a very strong and solid mathematical foundation to reach that. I'll just show very quickly one example of that in practice. So this is like Scylla, just one CPU, focusing on one CPU, and those spikes that you see there are mem table flushes. Mem tables that are being flushed to disk. The CPU scheduler is still providing some isolation, but it's set, for instance, statically to say you can only use half the CPU, but turns out half the CPU is too much because it flushes very fast. Ideally, what I would like to do is that if I have all that spare CPU, I want to spread that out throughout the entire time. And this is based on one example before and after the controllers. So the controllers are something new also in Scylla 2.2. Together with the CPU scheduler, not only I'll be able to isolate workloads, I'm also able, with a solid mathematical foundation that we developed, to automatically determine what is the best rate for those things to do and to go. Again, results from that is latencies are down even more on the higher percentiles, and they're closer to each other. There is less tuning. This is one example of the controllers running compactions. You can see that the yellow line here, the green line is the throughput of the system, and the yellow line is the amount of CPU and the percentage of CPU the compactions are using. And it starts growing and growing and growing until at some point stabilizes and your workload is fully smooth. And if that happens to change, because that's the big problem with tuning. The big problem with tuning is that you tune for one workload, the workload changes, it's all gone. But with Scylla, you don't have that problem because those algorithms are dynamic algorithms. So if the workload changes, automatically the database will figure out what is the best level for compactions for this workload. And your latencies might budge a little bit because the workload is different, but you can see that they're still very bounded. You can't probably see the numbers from there, but the green line here is my average. The green line is my 95 percentile. That's around 1 millisecond for this workload. The yellow line is my 99, around 2, and the 99.9 is also around 2. And those are all examples in 100% CPU utilization. So the system can guarantee isolation between parts and figure out at which rate to run them. Now, I skipped through this very fast. A lot of those talks are also available online if you want to see more. In our website, there is a lot more material. And I do thank Aaron for allowing me to have those final moments. I really want to tell you how Scylla does those things. And if you have any particular questions, you can get back to Aaron. You can also ask me more questions, whatever I can help you with.
Any questions?
There's one question right there.
So, you say that you have your own IO scheduler and also CPU schedulers. Does it mean that you have your own Linux kernel?
No, we don't have our own Linux kernel. So what happens, for instance, as I mentioned, with the Linux kernel, we just go to that proc file and we set the schedulers to no op. And then on top, we do our own thing. The CPU scheduler is a very similar thing because the thread per core design on itself already has just one thread running in that core. And the Linux scheduler is not really doing much. And the tasks, I actually skipped that slide, but the tasks that we have, they're fairly small tasks that this reactor is jumping one from one to the other. The scheduler, we just really separate them in groups, tag them properly, and then use the controllers to figure out which to run, for how much, for how long, and according to all of those priorities. Yeah.
So you just switch off the OS?
The OS is there, but it's not really doing anything. It's one entity. The same thing goes for the memory allocator. I go and we allocate 93% of your memory, leaving 7% as a reserve. And then I do my own allocations.
Okay. We have time for one more question? Anybody? Yes, no?
Awesome. I guess we'll be outside and we can still chat.
Okay, so Glauber, door, wherever you are in the room, is right over there, outside the door. And Aaron are here for one-on-one questions right now. I want to thank you all for coming and have a wonderful evening. Thank you.